Welcome. We are going to continue our lesson on Newton's second law problem solving with problems involving friction. Today's example involves angled forces. So take a moment and read the example here. We have someone at an airport pulling their suitcase with a strap across level ground at a constant speed. As usual, we want to start all of these with the free body diagram. So let's take a look at what that would look like for the suitcase here. We have our trusty weight, and I'll tell you what, for the sake of time, I'm going to pause and write this out. I encourage you to do the same. I hope that you have identified all of the same forces that I have. Weight downward, normal force upward, tension from the strap, although I called it a cord. Okay, I called it a cord. And then finally, of course, the friction force. So, since we already had S for suitcase. Now, what you may not have is you may not have the relative lengths of the arrows in the same way that I do. So, I'd be willing to bet that you drew a normal force that was significantly larger than mine. Okay, and we want to talk today about why the normal force is so short. Okay. What I want to do now is remind you of another skill that you have, and that's called componentizing. So if you remember, we can't really go forward with this type of free body diagram until we have componentized. Okay, we're going to use our typical coordinate system direction. To the right is positive and up is positive. And so what we need to do here before we can proceed is we need to make every force that's not aligned with either the y or the x direction, right, with one of our coordinate axes, we need to componentize them so that each of the components do align with one of the coordinate axes, right? So what you need to do is imagine the right triangle of which this tension, right, this angled force is the hypotenuse. So I'm going to sketch that in now. All right, that's going to look something like this. Okay, so for her to pull at an angle, it means that she is pulling both to the right and she's pulling upward, right? Something like that. Now, unfortunately, I didn't quite draw this angle at 55 degrees, right? 55 degrees is greater than 45, so we'd expect it more than halfway, but alas. Okay, so hopefully you remember your trigonometry here, right? This horizontal side is going to be the value of the tension, right? The hypotenuse, which is 35 degrees, times the cosine of the angle, right? 35 cosine 55, right? Cosine being adjacent. And then here, it's a little bit tight, so I'm going to bring it down here. That side, remember, components have a direction too, so that's pointed upward, right? That's going to be 35, think about it, 35 sine 55, that's right. Okay, so now we have componentized our angled force, okay? Now let's go back to why this normal force was less than the weight. That's because you are pulling upward, or when I say you, I mean the woman in the suitcase, right? She, by having her strap at an angle, is providing an upward force right here that's helping support the weight of the suitcase, right? So the full weight of the suitcase no longer has to be supported by the normal force. It gets some help from the strap, so to speak, and therefore the normal force gets to be less. By the way, just one more comment here. Nothing I've done here is new today, right? It's taking existing skills that you have already developed and applying them to a new problem. All right, we have done the hard work. Right now, for the one last big step in your brain, and that is to take this concept of the free body diagram and translate it into a set of equations that you can solve mathematically. So we'll go to the next screen for that. Now I will simply read my free body diagram into the equation. On the y side, there are three forces: the normal force from the ground, and the vertically upward force from the strap, which we identified already to be 35 times the sine of 55, and then we have the weight downward, right? And because the suitcase is at rest vertically, right, it's not moving upward or downward, we are balanced in the y direction, and the acceleration right here is 0. Guess what? The forces are also balanced in the x direction. There's a little piece of information in the problem that tells you that indirectly. Hopefully you're training your brain to catch that. That's right. The object's moving at a constant speed. So we take our two forces in the x direction and we set them essentially equal to 0 as well, right? Because the forces are balanced in the x direction, moving at constant speed. So the last quote-unquote new thing here is simply to solve in your newly minted tool, and that is the formula for the force of friction. So this number here comes out to 20.1 if you put that in the calculator. And then here I'm going to substitute in mu times normal, right? Now remember, coefficients of friction come in different varieties, so which one are we after here? That's right, we're after the coefficient of kinetic friction because we're moving. And we see here one of the features of friction problem solving, which is that we have a force that shows up on the x side that actually comes from the y side, right? So when you're doing friction problem solving, you're always having to work on the y side first to get the normal force, so then you can come over and substitute it into the x side equation. So we're really transitioning now out of the physics thinking phase and into the math solving phase, right? I'm going to do a few more steps for you, and then I am going to let you finish the problem. We have our normal force. This works out to about that number. And then here we have, if you remember, force of weight is mass times acceleration due to gravity. And that comes out to, that's 20 times 9.8, it's 196 newtons. Okay, so when you solve this, you get 167.3 newtons. And notice that that value is, in fact, less than the weight, right? Remember we talked about the normal force in this problem being less than the weight. The weight is 196. If the suitcase were just on level ground, then the normal force would support all of the weight and be 196 newtons. But in this case, because of the upward pull of the strap, we get a normal force that's a little bit less than the weight. Okay, so this number, right, will now come over here into this equation, and you can solve the equation on the on the left side for the coefficient due to friction. So I'm going to leave that to you. Good luck, and we'll see you next time.